Welcome to the Crazy Hat Chemist. So another video here on thermochemistry. But don't forget, check out the t-shirt and you can even donate to my website and get a sticker. Super cool. Put that on your hydro flask. It's just like the t-shirt, but miniature. Alright, so let's get started with this thermochemistry video. So 1, 2, 3, bam! So today's thermochemistry calculation number 3. I'm going to read the question for you. So here we go. What is the temperature of water when a 120 gram iron weight, specific heat capacity of 0.473 joules per gram degree Celsius, is heated to 125 degrees Celsius and placed into a calorimeter containing 225 grams of water at 25.0 degrees Celsius? So the question is, which equation are you going to be using for this problem? So this is the equation. It's the Q of the metal plus the Q of the water is equal to 0. That is, this is the heat of the metal is equal to the heat of the water, but opposite in sign. That is, they sum up to equal 0. So it's the same amount of heat is transferred from the metal to the water, and that is thermal equilibrium. And that is when their temperature, their final temperatures are going to be the same as when thermal equilibrium occurs. Heat always flows from the hot object to the cool object spontaneously. All right, so what is Q? That is the question. Q is equal to mc delta T. Q is equal to mc Tf minus Ti. So what I'm going to do is I am going to substitute into this equation what Q is equal to, which is mc Tf minus Ti into the metal and also into the water. So then we're going to rewrite this equation, get rid of the Q's, and have the mc Tf minus Ti for each the metal and the water, and their sum of those two is going to equal 0. So here we go, right here. So this is our equation. I've got, with the little subscripts are for the metal, the little W subscripts are for the water. So I've replaced each of the Q's on the left-hand side here. I'm going to start on the left-hand side. It's M for the mass of the metal times the specific heat capacity, that is the CPM of the metal, times the final temperature minus the initial temperature of the metal, plus the mass of the water times the specific heat capacity of the water times the final temperature of the water minus the initial temperature of the water. The sum of the heat of the metal and the sum of the heat of the water is equal to 0. That means that they are the same value but opposite in sign. That is when they reach thermal equilibrium. So from the numbers that are given in this problem, we need to figure out where those numbers belong in this giant equation here. It looks complicated, but you're going to do this one step at a time, very slowly and carefully. Okay, this is the mass of the metal. That's a 120.0 grams iron weight. That's the mass of the metal. That's where it's going to go right there. We also got the specific heat capacity for the metal. That's that iron weight. That's going to go in the CP for the metal. That's 0.473 joules per gram degree Celsius. Okay, we also have the initial temperature of the metal. That's at 125 degrees Celsius. Okay, so that metal was heated up to 125. That's why that's the initial temperature. Okay, then that metal is placed into a calorimeter containing water in it. Okay, and that water's mass is 225 grams. Okay, all right, now the specific heat capacity for water is a tabled value, or you should have memorized it by now. That is 4.184 joules per gram degree Celsius. You got to know that value. That is the same thing as the specific heat capacity for water, but in calories, which would be 1 calorie per gram degree Celsius. Okay, all right, now the initial temperature of the water is the 25.0 degrees Celsius. Okay, so that's the temperature of the water initially. Now, the question is, what is the final temperature of the water after the metal and the water have been mixed and this reaches thermal equilibrium? Well, that is what we are solving for. And you notice there that I've included in the red what we are solving for. And we're solving for the final temperature of the water and the final temperature of the metal. In fact, these two numbers are the same because the final temperature of the metal and that of the water is the same when thermal equilibrium is reached. And that's the important conceptual portion of this question that you need to understand before carrying on. So now what we're going to do is we're going to plug in those values into there, just like I have outlined for you with the colored arrows. And that's what I've done right here with all the appropriate units. So I have 120 grams times the specific heat of the iron, that's 0.473 joules per gram degrees Celsius. We have the TF for the unknown that we're solving for, which is the final temperature. And then the 125 degrees Celsius is my initial temperature of the metal, plus the 225 grams of the water times its specific heat capacity of 4.184 joules per gram degrees Celsius, times the final temperature of the water, of which, again, we are solving for, minus the 25 degrees Celsius, and this all sums up to equal 0. So how are we going to do this mathematically? So the first thing that we're going to do to make this as simple as possible on you, now you do know that you're solving for a final temperature, so therefore the units of what you are solving for are going to be in degrees Celsius. So since we know the units of what we are solving for, what we're going to do is get rid of the units and only focus on the numeric values of which we have. That should help you out solving this algebraic equation here. But in order to help you out just a little bit more in solving this algebraic equation, we're going to take this 120, that is the mass times the specific heat capacity, and then we're going to distribute it over the final temperature and the initial temperature. We're going to do the same thing that of the water, and that is the mass times the specific heat. That product is going to be distributed over the final temperature, which is going to be X, and the initial temperature of the water. So I'm going to plug in those values, getting rid of the units here, and then we'll pop the units back in after we solve this algebraic equation. So the product of 120 and 0.473 is 56.76. I've replaced the TF with X, so that's why that's in that parentheses minus the 125, plus 225 times 4.184, the product of that is 941.4 times the quantity X minus 25. Now, again, you're going to distribute the 56.76 with the X and the negative 125, and then distribute the 941.4 with the X and the minus, or the negative 25. And that's what I've done right here. So now on this step, I've distributed what's on the outside of the parentheses, just like my math tells me to do. And so I have 56.76x minus 7,095 plus 941.4x minus 23,535. This all sums up to equal 0. So I need to combine my x terms together and my non-x terms together. What I'd highly recommend you do is make sure that you keep the sign that's in front of the number. So I've combined the x terms and the non-x terms. My x terms sum up to 998.16x. My non-x terms is negative 30,630. I'm going to move that 30,630 to the other side with an addition on both sides of that. And what I get is 998.16x is equal to 30,630. I'm going to divide both sides by the coefficient in front of the x, which is the 998.16. And this is the number that pops up in my calculator, which is 30.6864. I'm going to look at the original numbers in the problem, and I'm going to look for the number of significant figures of which I started off with numerically on this problem. Okay, and the fewest number of significant figures I have is 3. So I'm going to round this 30.6864 to 3 significant figures, and I'm also going to put back in there the units of what are x. The units of x is degrees Celsius because it's a temperature. So 3 significant figures, and my number rounded to 3 significant figures, which would be 30.7, and I've plugged in my units, which is degrees Celsius. So you also need to, before you just keep on going and plug in these numbers randomly in your calculator, you need to be thinking about, does this number make sense? That's the other part that you need to be thinking about in chemistry. This is not just a math problem. It is a math problem with an application to it. and that is the initial temperature of the metal was 125 degrees Celsius. The initial temperature of the water was 25 degrees Celsius. So I certainly cannot get, after mixing the metal, which is hot, with the cool water, I cannot get a final temperature when it's reached thermal equilibrium. That's when both temperatures are the same. That is less than 25. That is impossible. Nor can I get a number that is greater than 125. That is also impossible. Okay. Furthermore, you should be thinking about the product of the mass and the specific heat, and that will give you a relative idea of where this number belongs between the 25 and the 125. So a number in between 25 degrees Celsius, the initial temperature of the water, and the final temperature, and the initial temperature of the metal at 125, somewhere in that range would make sense. The 30.7 is in there. However, to refine this a little bit more, you need to understand that the product of the mass of the water and the specific heat, that product is greater than the product of the mass and specific heat of the metal. Therefore, the final temperature will be closest to the greater product. And the greater product is the mass of the metal and the specific heat, the greater product is the mass and specific heat product of the water and not the metal. So that's why that number is closer to the 25 and not to the 125. All right. I am the Crazy Hat Chemist, and I've got a crazy hat. Hopefully you enjoyed that video. Give me a thumbs up if you do. Subscribe to my YouTube channel. Pass on my YouTube channel to all your friends. Subscribe to the YouTube channel. Look on my website. Find my website. Donate to my website. Get a t-shirt or maybe even a cool sticker. See you next time. Bye for now.